Good afternoon. My talk will be about testing and reusable build automation using Tekton. We will zoom into a little bit of the picture that Andreas already has shown you before in the previous talk. First off, who am I? I'm Pieter Vincken. I'm a consultant at Ardina. I work as a cloud automation engineer for one of their customers. I have a background in software architecture and development, and I'm mostly interested in automation, any kind of automation in IT, using the public cloud in enterprises, and running hyperscale software. 30 years old, and in the slides, which I will share later on, you can find the links to the company blog and my LinkedIn if you have questions afterwards. So the agenda for today is, first of all, I will start with explaining what is build automation. You will see some parts are, we will dive a bit deeper than what Andreas already showed, but there will be some similarities as well. And then the second part of the talk will be about how we can use Tekton to actually do your build automation, so to build your artifact, and how we have set it up. So as Andreas mentioned, there's no one way to do Tekton properly, but I will show you one of the ways you can do it. And then we will end with some lessons learned adopting Tekton at a large corporation at my customer, basically. If you have questions, I will try to monitor chat on a separate window. So if you have questions, just pop them in there, and I will try to answer them either during the talk or at the end, if there's time. So what is build automation? So we will focus on the first part that Andreas showed, what actually in his setup was solved by build packs. So you have a commit on a Git repository, and the developer sits behind his laptop. He writes some code for his amazing application. He does git push because he's satisfied that his new change will work. That is submitted to his source code repository, and that triggers some magic. And at the end of the magic, there is some artifact, in this case maybe a Docker container, that is published somewhere for somebody else or for you to use and to deploy to somewhere so that that code can run. So that's the packaging and something that can run somewhere. What do we commonly see at customers as solutions for this? We see Jenkins, gladly and unfortunately everywhere. We see a lot of GitLab, a lot of TeamCity. If you're on the Atlassian stack, you might have seen Bamboo. And one of the things that we're adopting in JWorks currently is Azure DevOps, which is a SaaS offering by Microsoft. So maybe let's take a step back. Why is build automation actually important, and why do we need it? Well, the alternative of not having build automation is to create artifacts ourselves manually. So locally on a developer laptop, you run some scripts, and magically there is an artifact at the end of that. The problem with that is if you want to do it consistently across multiple systems, you have to configure every system identically, which is especially on a developer laptop where everybody tends to install different tools to solve the same problem. And that's quite hard to do that consistently. So consistent artifact creation is one of the things that a build system can solve for you. If you have ever built a not so modern application locally on your laptop as well, then you have noticed that, probably noticed that the build process is not lightning fast. It will take up quite some resources and might block your laptop for a few seconds up to a few minutes if you're lucky. So we want to offload that from developer laptops as well to make sure that they can just develop and make changes and improve the business logic and not focus on or not taking a coffee every single time that they need to build something. A side effect of using build automation, it's not really a reason to use it, but a side effect is that you have the ability to enable automated testing on every single code change. So again, if you build the artifact locally, you don't know which steps somebody executed before pushing that image to some shared environment. So in the pipeline, you can enable automated testing built in. It also improves the scalability of building applications, again, because you can have multiple people working on the same application. They all make changes to the same code base, and that artifact is created every single time with all the changes that are current in the repository. So you don't have to pull in changes before you build it and then submit the artifact again. It's always based on the latest information that's available in the source repository. The next one, repeatability, is more of an auditability standpoint. Because your artifact creation is fixed, you can also recreate it later on. So for instance, if you have to recreate the same artifact for auditability reasons, or you have to recreate it because you need to check something later on, that's always possible because you have a definition on how to build it. And again, continuous integration that ties in together with the automated testing. Now, this is a bit of an old slide. It's a bit weird that we have to not defend this, but in some companies we have to. Why do we need to test build automation? And I've seen time and time again that the software stack is tested, and it's tested extensively. We use a testing pyramid to actually properly test our applications, so our actually runtime applications. But I haven't seen a lot of companies where they actually test their build automation in a structured way. So writing test code for your build automation, that's not a common thing. While your test or your build automation is still just code. It's software like any other. And the same principles apply why you want to write test code for your normal application. Those same principles apply to your build automation. You also want to simplify debugging. You can write an error case in your test, and once that error case is solved, that test should be green. You also have more consistent rollouts because you can, every time you make a change, you can run all of the tests as a regression test and make sure that you haven't introduced any regressions. It also eases the development process because, again, just like normal software development, you can write a test and then start implementation. Once all the tests are green, you know that your feature is done. And of course, I don't have to explain that code quality or your software quality in general improves if you write tests for your build automation or for normal software. So how do we test? And this is a bit of this is an opinionated way of doing it. If you have a different build system or a different approach, that's perfectly fine. But we tried to map the simplest of testing pyramids on top of our build system. So we start on the left with unit tests, which validate some business logic, just like you would with a normal software. And we map that on top of one build step. And a build step is a bit of a vague term to describe just a single action you execute in your build system. Now, what that defines is a bit dependent on your environment and your use case. But it should execute some business logic in your build automation, and it should just do a small thing, the smallest thing you can test, basically. For instance, if you update a file somewhere, or if you determine a version number, or you create a unique name in your pipeline somewhere, or you update some files somewhere, that should be your one single testable component. Those unit tests should be runnable locally, so you should not depend on any components of your build system. And what you, of course, shouldn't test, again, just like any other unit tests, you should not directly test integrations or external tooling. So, for instance, if you do a Docker build, you don't need to test that your Docker build works. You just need to test that you can actually make a call out to the system. And you validate the output of what is being executed. So again, standard rules for unit testing. The next phase in the testing pyramid is integration testing. And here you would test that these components that you tested in the unit test, that they tie together correctly. So that if you execute 5 steps, that you can actually execute those 5 steps in order, but also that those 5 steps create the desired outcome. So that the outcome would be some side effect in an external system. And you would mock away integrations if possible. Sometimes that's not possible. And you just have to use the real system. But if it's possible, just mock away the integrations. And you would use a specific set of test input. Again, I don't think I'm telling anything new here. This is all standard stuff for integration tests. For instance, an image build could be an integration test where you want to test that you can log into the registry, build an image, and then push it. And the thing you would test at the end is actually that the image was built successfully and pushed to the registry. You don't really care whether or not the login worked, because if the image ended up in the registry, you know that the login worked. Because you are dependent, or you are probably dependent on some integrations with your build system, these type of tests should only run within your build system. If you can make them run locally, that's even better, but they should at the very least run within your build system. And then finally, the hardest test to always write and create, either in software or in build automation, is end-to-end tests. So those should validate a complete end-to-end pipeline. So that's from a code change to some artifact created somewhere and stored somewhere in an external system. So for instance, an application build where we do a Spring Boot, where we write a Spring Boot service that's built, packaged, and submitted to a Docker registry as a Docker image. It should validate the execution of the tasks, so it should not validate any outcome or any other side effects anymore. It should just validate that the tasks were executed and they were executed correctly, so in the correct order. It uses real integrations, so no mocking of services here. And again, these are probably only runnable in your build system. Those, if you can get these to run locally, that would be really nice, but probably you're dependent too much on the real integration, so you probably need to run those in your build system. So that's about the theory and about the what we want to do. Next chapter, or the next part, will be about Tekton. So what is Tekton? As Andreas also already mentioned, Tekton is a framework to build CI/CD systems. And because it's a framework, it's not an out-of-the-box solution. So they give you the nuts and bolts, but you still need to build the entire system to actually support your CI/CD solution. It's a spin-off of the Knative project, so it originated from there, and it's backed by Google, IBM, Red Hat, Pivotal. Basically, all the big players are basically in this. It's also part of the Continuous Delivery Foundation, so that means that it has quite good governance, and it's also part of the consequently governed by the Linux Foundation. As already mentioned by Andreas as well, it's actually core to the Jenkins X and the Jenkins X project. So they use Tekton to build their parts of their solution. And it's also used by OpenShift to support their OpenShift pipelines solution. Tekton, as any good software in 2021, is split into multiple sub-projects. So you have a dashboard, which is basically UI for information that is available in the Kubernetes API. You have Tekton triggers, which is Tekton's connection from the outside world into Tekton. So any external events that occur can be captured by the triggers component and then used to trigger a pipeline in Tekton to execute some action in Tekton, basically. And then the most important one is pipelines, which does all of the magic that we saw earlier. So it's actually manages all of the state and the translations that need to occur once you submit a pipeline and you actually want to run something inside the cluster. And finally, of course, Tekton runs on top of Kubernetes, so any Kubernetes distribution is supported. Most notably, OpenShift Pipelines uses Tekton, so it definitely runs on OpenShift as well. So what problem does Tekton solve? Again, because it's a framework, in itself, it doesn't fix any problems. It probably gives you a couple of more problems to solve. But it provides you with a great building block of making a tailor-fit solution. So it's highly customizable and highly configurable. So they don't have any opinions about how you should run your pipeline, what components need to be connected, what language you should use to run your pipeline. They don't make any assumptions there, so they give you complete freedom to actually create some definitions on top of Kubernetes pods, basically, and they facilitate on automating and governing these resources. Tekton is also claimed to be highly scalable. They are working on this. There is so you can scale it across a huge Kubernetes cluster, that's not the issue. But they have some issues with having a lot of resources in the cluster if you don't clean them up properly. So for instance, if you have more than 10,000 pipeline instances, then the reconciliation becomes too slow and it basically dies currently. But they're working on this, and that should be hopefully improved once we hit 1.0. It's a Kubernetes native solution, so it's heavily integrated with the Kube API. It uses custom resource definitions to actually define all its components and to keep it state. So if we can use a metaphor, Tekton is the right ingredient to make a fantastic meal, but of course you still need to cook it. Now I will have to ask you for a little bit of attention for 3 slides to provide you with some terminology. It's a bit dull to explain, but it's really needed to understand how Tekton works and further down the presentation. So the smallest component in Tekton is actually a Tekton step, which is nothing more than a container definition. It has a container image and a command, and it runs until completion. So you define something, you define a container image and a command that will be executed on your in your pipeline. And the step is actually part of a task definition. So you don't define a step as a separate resource, but you define it as a part of a task. Then the next abstraction that they have is a task, which is a set of steps which are executed in order. And a task is defined as a single component. And in our case, what you need to, if you implement Tekton yourself, you will have to see what fits for you best. But the task in our context is something that is usable on its own. So a step is not usable on its own, but a task is usable on its own. So it promotes, you should be able to reuse that, for instance, in a separate pipeline. For instance, a git clone is a good example where you have a task where that you can reuse across multiple pipelines, but that might consist of a step where you create some git configuration and then a step where you actually execute the git clone. It directly maps on top of the task directly maps on top of Kubernetes pod, so you will see that the definition of a task and a pod are actually very similar. And then the last level of abstraction is, of course, a pipeline, which is just a set of tasks, which again are executed in order with that in mind, that you can define dependencies between tasks. So if you have 3 tasks, A, B, and C, and you tell Tekton that C can only run after A is completed, then you just define a depends on that C can only run after A. Pipelines are also defined as a single component, as a custom resource, and we implemented it as a pipeline is a set of tasks that produce an artifact in an external system. So you go from a single line code change into an artifact in an external system that is ready to be deployed. That's our definition. Again, it's not specifically what Tekton says, but that's what we use. Just like Kubernetes has the deployment, replica set, and pod definitions, where you have the deployment which defines what you want, and the pod actually shows you what is actually running. Tekton has a similar setup where they have a task which defines what you want to do, and a task run is the actual execution. So in the Kubernetes API, there's a task run resource if you install Tekton, and that's used by the Tekton operator to see what's currently running, in which state it is. And it's basically a copy of the task definition, but then applied for an execution. And the same goes for a pipeline run. It's the actual execution component of a pipeline, which is used by the Tekton controller to keep the state of a pipeline. So it will have a status running or canceled or completed. And that's used by the Tekton controller to keep track of what is happening inside the cluster. I mentioned earlier that there was a triggers component. That's also important to know. So the trigger is a component that handles the external events. So for instance, a webhook, if you use, for instance, Bitbucket like we do, that can be used as a trigger to start a new pipeline. The component allows for some filtering. So for instance, if you have a Bitbucket trigger coming in, you can filter that you want to also fetch the branch name, and you want to know who committed it. So there's some flexibility there. And a trigger definition, it uses two resources. And the first resource is a trigger, which connects the external event to starting something in Tekton. And that something you start is actually the trigger template, which in most cases is just the link between a trigger and a pipeline. So you define if this trigger comes in from Bitbucket, you need to start this pipeline. That's basically what the trigger template does. So final slide of terminology, just hang on 2 more minutes. One important concept, and Andreas already mentioned that earlier as well, the workspaces in Tekton, which are both really pleasant to use and a pain to manage. They're basically a shared folder between tasks in a single pipeline. So we've opted to use persistent volume claims or persistent volumes to back these, but you can also use block storage. You can also use other solutions like even an empty directory, so just node space basically. That's also possible and to back this, but a persistent volume makes sure that you share this between tasks and make sure that that state is kept between tasks in a single pipeline run. The workspace is defined in a pipeline and in a task. So you, on a pipeline level, define I need to have a workspace, and you pass the workspace to the tasks that need to use it. And when you start a pipeline, you define what needs to back that workspace. So for instance, you can start up, you can define that you need a workspace to store your source code. And then when you start the pipeline, you define, okay, this workspace needs to be backed by a persistent volume because it needs to live for the longevity of the entire scope of the pipeline. But you could also say, if you, like Andreas mentioned, you want to use a cache, then probably it needs to survive your pipelines. So you might use something like block storage to back your workspace. Final piece of terminology, and it's actually the easiest one. It's controllers. Tekton uses controllers, just plain Kubernetes controllers, which execute control loops, and they reconcile the cluster. So that means if there's a definition of a task run, for instance, then that controller will look at that state and try to reconcile that into some pod definition. So how does the workflow look in in Tekton? So you start with a git push. So like we mentioned earlier, you commit something to a code repository that triggers your build. That is committed to your source code repository. That triggers Tekton triggers with a webhook. There could also be some other eventing mechanism. Tekton triggers actually supports quite some eventing mechanisms. But that triggers Tekton triggers, which was an excellent name. Triggers then uses the template that we mentioned earlier to create a pipeline run inside the Kubernetes API. And that Kubernetes API keeps that state, so it's stored in etcd basically. Then Tekton pipelines, so a different component of Tekton actually monitors the Kubernetes API for any pipeline run resources. And once it receives the pipeline run created event, it will read the pipeline definition and then create task runs associated with the pipeline. So if we take the example of earlier where I said we have 3 tasks, A, B, and C, and A and B don't have any dependencies, so it will create task runs directly for those and get those tasks started. And it won't create one for C yet because that's dependent on A, and A was not completed yet. So that's the setup a bit how Tekton Pipelines does that. The next step is then once a task is created, the Tekton Pipelines component is actually a little bit schizophrenic because it creates the pipeline run here, submits that to the Kubernetes API, and then actually waits on a task run to actually reconcile and create a pod definition. So the Kubernetes API is there in between the 2 parts of the Tekton Pipelines component. And once it gets the task run, it then creates the pod definition and submits that to the Kubernetes API. And then the pod runs like any normal pod in Kubernetes. So it runs the init containers first, then executes the running pod. And once it completes, again, the Tekton pipelines component gets the event. It sees that, and then it updates the task run component, the task run that's associated with that pod to have the status completed. Again, that's submitted to the Kube API. Again, Tekton pipelines is a bit schizophrenic. It waits for the task run completed event, and then it looks at the pipeline. Okay, what's the next step that I can execute? A and B have now been completed. What's the next task run that I can start? It creates C in the example that we used. So the task run C gets submitted and the whole chain starts again. So this shows how Tekton uses actually the Kubernetes API to constantly reconcile its own state, and how the different steps or the different tasks in Tekton are actually completely disconnected from each other. The only thing that connects them is actually Tekton once there's an event on one of them completing or failing. So I promised, I have 8 more minutes, I promised I would show you how you can do testing with Tekton as well of your build automation. So again, we have our testing pyramid with the 3 different levels. The unit tests, actually, they map quite nicely onto a single Tekton step. So you submit some information to your step. It generates some effect on your input, and then you validate the output. Since a step is only a single action or a single command in a Docker container, or even executing some script in your step, you can just use any testing framework, be it some kind of testing for Bash specifically, or even for Python. We have some steps which have some Python code behind them. We just used a Python framework to actually test that. So then you can test your business logic in the unit tests. The next level is the integration tests, and those we map directly onto a single Tekton task. So you would execute all steps in a Tekton task and validate that it has the expected side effects. And for this, you would use a custom pipeline where you have a pre-task which creates the context where this task can run. Then you execute the task, and then you have a post-task with validates, which actually maps directly onto the standard given when then testing methodology where that you can use. Then the last part is the end-to-end tests. So you would actually execute a full end-to-end Tekton pipeline using preferably real-world input. So you would use a real project if possible, because some automation might, because you might burn some version numbers, it might not be optimal to actually use a real-world project, but you can then potentially fork a real project, rename it, and then test it that way, so that you don't have the naming conflicts with your tagging strategy. And the setup for this would be having a test pipeline in place that starts the second pipeline, and you would only validate in that test pipeline that after your pipeline has completed, that all the tasks that you expect to be executed are executed, and that they were executed in the order that you expected them. So you wouldn't not test the side effects in this case. Final slide, or second to last slide. What did we learn? So we implemented the solution that the customer I work for. And one of the biggest lessons learned is that we need to treat pipelines and build automation in general as regular code. It's not because it's not running in production, so to speak, at some point, or not end user facing, that we don't need to treat it as regular code. We should still version our pipelines. We should still apply automated testing strategies to it, and we still should have a release cycle on how we treat or how we use pipelines, and when we release them to which customers. What we also notice is our application landscape also runs on Kubernetes, and actually moving our build system closer to Kubernetes, or actually running in Kubernetes, because before Tekton we were also on Jenkins with VMs. It made it a lot easier to have our tests run inside Kubernetes natively as well. So instead of having a Docker host on our Jenkins VM and then using Docker Compose to manage that, it's actually way easier to get Kubernetes or to attach Kubernetes resources to the test and then run our test that way. And the final point I want to make is that adopting tooling to assist in the adoption of a new technology helps tremendously. So we have two projects which I would like to highlight. One is Tekton, which actually originated from our own implementation, which helps you in making it easier to actually embed your pipeline into your application repository. So, for instance, if you have an application, Tekton doesn't really have a solution to embed the Tekton pipeline into your application repository, so it expects that to be separate. But Tekton actually solves that for you, so definitely have a look at that. And the second component is Renovate Bot, which is a really nice solution. It's similar to Greenkeeper, if somebody knows that from seeing it on GitHub, which basically allows you to automate updating your dependencies in a repository. And Renovate Bot helped us tremendously with actually getting our pipelines, because again, our pipelines are versioned. That means that if we update our version in the pipeline, every component that uses our pipeline needs to update the version definition in the repository. And Renovate actually made it possible for us to create PRs automatically for all our applications, do not have to do that manually. And it also pushed adoption within the teams quite significantly, because they could easily see that there was a new version of the pipeline. They would see immediately if that new version of the pipeline worked for their application or not. And if it did work, they could automatically merge that to master, meaning that they would have a new version of their component, and all new versions of their application would automatically use the new pipeline definition. So 2 more minutes left. So if there's any questions, please feel free to share them now in chat or to reach out to me later. If you, I will share the slides as well. If I can copy the link, find them here, or otherwise I will share them later through Gavin. If you're interested in these type of things as a JWorks employee, definitely join our Code to Cloud Competence Center. We're constantly looking for people who want to look into these things and adopt these. If you're a customer or somebody looking for a new job, then definitely reach out as well. We're always looking out for new talent. And as a customer, if you are interested, feel free to reach out. We can help you to adopt Tekton as well. Thank you.